Hi, welcome everyone to our special astronomy lecture this evening. This is a new collaborative effort between the Southern Vermont Astronomy Group, SOVERA, and the Middleman Observatory at Middlebury College. For SOVERA, this is their monthly meeting, and for the Middleman Observatory, this is the beginning of our new Middleman Astronomy Lecture Series. We're very fortunate to have transitioned to a virtual forum tonight in order to extend the accessibility and reach of this talk. In addition to numerous SOVERA members and Middlebury students, we have Middlebury community members, Middlebury faculty and staff, Middlebury alumni, amateur astronomers, other astronomy and space curious individuals from New England and beyond, as well as students from high schools and colleges in the region, including many from Middlebury's partner institutions in the Keck Northeast Astronomy Consortium. My name is Jonathan Kemp, and I'm with the Middleman Observatory here under the dark skies in the lovely Champlain Valley of central Vermont. After a few additional tech notes, I will then pass it off to Pat Porch of SOVERA to introduce tonight's speaker. At the end of the evening, Eric Schmidt of SOVERA will handle questions and answers from the audience. I would like to briefly mention some technology notes and rules of the road before we get going. This lecture will be recorded, but attendees do not have video enabled and will only potentially have audio enabled for questions at the end. If you have technical questions, please use the chat function to connect with our panelists who are hosting the event. If you have astronomy or other subject matter questions for the speaker, which we highly encourage, please use the Q&A function. You can also upvote questions or comments from others in the Q&A area if you see some things that you would also like addressed after the lecture. You may ask a question verbally at the end of the lecture using the raised hand capability within the participants window. The chat feature, the Q&A feature, and the participants functionality should all appear on the edge of your webinar window. While we are very happy to welcome students of all ages, minors and other younger students should please have permission of a parent or guardian before participating in tonight's lecture. But again, we welcome students of all ages. Lastly, please remember to share respectfully and with civility as we begin tonight's talk as a community. And I would now like to introduce Pat Porch of SOVERA.
Thanks, Jonathan. I'd like to welcome all our viewers. Hopefully everybody's staying safe and healthy during these unprecedented times. We're excited tonight to have Dr. Heidi Hammel, who will be talking to us about the James Webb Space Telescope project. Dr. Hammel brings to us an extensive and impressive amount of experience. She received her undergraduate education at MIT and her Ph.D. at the University of Hawaii. She then held a postdoctorate position at JPL, where she was part of the imaging science team for Voyager 2's close encounter with Neptune. Great way to start a career, huh? She then went back to MIT, where she served 9 years as a principal research scientist and for the Department of Earth, Atmospheric, and Planetary Sciences. Spent many years with the Space Science Institute in Boulder, Colorado. She currently is Vice President for Science at the Association of Universities for Research in Astronomy, also known as AURA, and is one of 6 interdisciplinary scientists for the Webb project, and thus will be guaranteed observing time with Webb once it goes online. She has observed with many major telescope facilities, including Gemini, Keck, Spitzer, and has used the Hubble many times. She's received numerous awards and recognition for her work and her outreach, and was also featured as part of a series in Newsweek. Tonight, she will give us an update on Webb status and talk about how she and her team will utilize Webb for her research. At this point, I'd like to turn our virtual stage over to our featured speaker, Dr. Hammel. Thank you for joining us tonight.
Thank you very much, Patrick. And I'm going to start sharing my screen, and I hope we'll all be able to see that. And if my host can give me a thumbs up that it looks good. I'm assuming that it looks good.
We are all good there, Heidi.
Fabulous. Okay, great. Thank you so much for this opportunity to share my love and excitement about the upcoming James Webb Space Telescope with you. My team is going to be looking at solar system objects with the James Webb Space Telescope. So this background is a fanciful montage that one of my team members put together showing the backside of Webb, looking at all kinds of stuff in our solar system. I'm going to answer a lot of different questions today. We're going to make some digressions into some physics, We're going to talk about light and spectroscopy, but we're mostly going to talk about the exciting science that we're going to do with Webb. So we're going to start by talking about who was James Webb, because I get asked that a lot. Why do we need Webb? What is Webb? What will Webb explore? And then focus on Webb in our solar system. And at the very end, I have a little video that was done by Hank Green about James Webb Space Telescope to talk about whether it's worth it or not. So who was James Webb, and why is our telescope named after him? James Webb was the NASA administrator from 1961 to 1968. And in that role, he was the architect of the Apollo space program. He was the person who took this from a conceptual idea to actually getting people to the moon. Now, those of you who know this know that we landed on the moon in 1969. So he stepped down just before that happened for a variety of reasons. But he was the architect. More importantly for scientists, he initiated our space science program at NASA. And during that tenure, in those few years in 1968, more than 75 space science missions flew. And so he's a worthy person to name our telescope after, because he truly believed in the science that NASA could do, not just putting flags and footprints on the moon, but treating NASA as a true science agency. So that's who James Webb was, and that's who our telescope is named after. Now, why do we need Webb? We have lots of telescopes on the ground and in space. You know, we have so many telescopes. So why do we need a new one? Why do we need Webb? To answer that, I'm going to have to go into some physics. We're going to have to examine light. And this is some background material, especially for the students here. There's more to light than meets the eye. Isaac Newton did a fabulous experiment where he took a prism and put it next to a pinhole in the wall, and the white sunlight spread out into a rainbow by the prism. One of the things that we since learned is that light doesn't just stop at red or stop at indigo at the other end of the visible rainbow. Light extends to longer wavelengths and shorter wavelengths. And so we have names for this light, and you've heard these names. You've heard of radio, microwave, UV, X-rays. Those are all kinds of light. And our eyes only see the visible part, but the universe emits light at all of these wavelengths. So astronomers want to study all of these different colors of light. And so we have astronomical observatories that cover the full electromagnetic spectrum. Hubble is a visible wavelength telescope. Webb, I'm going to call it Webb because that's what I'm told to do by NASA. Webb will be an infrared optimized telescope. We also have radio telescopes and we have gamma ray telescopes. But why red? What's important about that? Here's a picture of a guy holding up a garbage bag, right? And at visible wavelengths, what you see is a guy holding up a garbage bag. But if we had infrared eyes, we could see right through that garbage bag. The longer wavelengths of light penetrate through that and allow us to see things we cannot see with visible light. And this is important in the universe because there are things that are filled with a lot of dust, which is the equivalent of that garbage bag. Here's a beautiful nebula, but if you look in infrared light, all that dust disappears, and you can see through the nebula to the very inside of that star-forming region, and you see jets, and you see other stars. So by looking in the infrared, we can probe to different wavelengths and see things we can't see otherwise. That's one really important reason. I'll come back again. Now, why does it have to be in space? Well, it's because we have an atmosphere on our planet, and it's a lovely atmosphere. It's there for us to breathe, but the atmosphere absorbs light. And so this cartoon shows you different wavelengths of light and shows you that if you want to get the infrared light, I'm going to bring my cursor, it's real tiny, but if you want to get infrared light where James Webb is sensitive, you have to put it in outer space because our Earth's atmosphere absorbs infrared light and it can't get to the surface. All right, so that's why we need to put this thing in space. Now I'm going to do an even deeper dive into a subtlety of light and matter. If you have that rainbow of light, even in the visible and extending, when we're looking out into outer space, some materials absorb the light. So if you measured the rainbow of light, there are colors missing. And other materials emit light. And so if you're looking at the rainbow, you'll see extra light at some colors. And this property of materials of absorbing light and emitting light is the astronomer's secret tool. This is the tool we use for exploring the universe. Now, back in the olden days, when we were first starting to do this, we did not have color printers. So there was no way we could publish beautiful rainbows like this. And so astronomers came up with a shorthand way of explaining that. They sort of said, we're going to draw a straight line, and if light is missing, it's going to go down. And if light is added, it's going to go up. And so these lines of wiggles and things are called spectra. And we astronomers use these all the time when we are exploring the universe. NASA hates spectra. NASA's technical term for spectra is wiggly line charts, and they never ever want to show them. But they're crucial for us. So NASA does things like this chart. This is a picture and a spectrum from the Hubble Space Telescope. And the picture is off to the side. It's the Eta Carina Nebula. It's an exploding star. And then spreading out from it is a spectrum where you see white lines of material. And they've been identified for you there. They're nickel and iron and argon and helium. By looking at the presence and absence of these extra bits of light in a spectrum, the squiggly line, we can learn about something's temperature, its pressure, its dynamics, its composition, so many physical parameters from things. Even though we can't touch them, we can measure these important parameters about them. So for an astronomer, the spectrum is everything, all right? So I will be showing you spectra of things, and they'll be the squiggly lines, but I want you to remember that it's light that's added or subtracted by the properties of the material that we're looking at. Really important. Now I'm going to tell you why this matters for James Webb Space Telescope. The top row shows you an example spectrum of a nearby star, and you see that there's black lines missing, and they're labeled in Greek letters, alpha, beta, gamma, delta, epsilon, all right? That's a nearby star. But if we look at a nearby galaxy, which is made of stars, if you look really, really closely, you will see that the lines are shifted a little bit to the red. I don't know if you can see that, but it's there. But if you look at a really, really distant galaxy, you went to a really distant galaxy, you can definitely see how those lines are all shifted to the red. And if you look at an extraordinarily distant galaxy, they're hugely shifted into the red. What does that mean? That means that if we want to look for the first stars in the universe, for the first galaxies in the universe, we can't look in visible wavelengths because those characteristic lines that we want to see in the spectrum are all shifted into the infrared. And therefore, we need a telescope that's optimized for the infrared to do this work. And that is why we have the James Webb Space Telescope. It is an infrared optimized telescope to allow us to probe the earliest stars that have formed in our universe. And that's all happening in the infrared. So that's why we're building Webb. Here's an example from Hubble. This is the ultra deep field of Hubble. So I'm not going to explain everything, but I want you to notice first, in just a sort of a rough glance, that a lot of these galaxies look kind of yellowish, right? Those are more distant galaxies. And if you look really, really carefully, I'm moving my cursor in a circle. It's circling a bright red object. That's a really super distant galaxy. That's the kind of target we're looking for with James Webb Space Telescope. And so this is the telescope itself, and I'm going to talk a little bit about why it looks the crazy way it looks right now. But it is a telescope designed to be a successor to Hubble, but it's going to be optimized in the infrared. That's a really important distinction. So what is it? What is this telescope? First of all, it's an international project. NASA is the lead, but we are collaborating with the European Space Agency. They have built one of the instruments. We are also collaborating with the Canadian Space Agency. They have built the fine guidance system that's going to allow us to point and navigate. Northrop Grumman is the lead contractor, and Space Telescope Science Institute, which is part of AURA, where I work, will be the Mission Operations Center. And this picture is an inset to give you a sense of scale of how big Webb is. This is a collection of people just at the Goddard Space Flight Center with a full-scale model of Webb. And those sun shields, which I'll talk a little bit about, you can see are the size of tennis courts. So this is a very large, massive telescope. How is it different from Hubble? Here's a little cartoon that shows you the mirror of Hubble versus the mirror of Webb. It sort of shows you Hubble and Webb to scale. And even though they're physically about the same size, you'll notice that the mirror of Webb, the shiny gold thing, is quite a bit larger than that of Hubble. And that's a really important thing. It allows us to see much fainter objects with higher sensitivity. So Webb is bigger than Hubble, but there are three other things I want to tell you about Webb that distinguish it from Hubble. It is redder, which we've talked about. It's colder, and it's further from us. All right. So let me talk about each one of those in detail. We've already talked about it being bigger. Here's another example. And in this example, you could see one of the things that's special about Webb. It isn't a single monolithic mirror like Hubble has to collect light. Webb is composed of 18 segments. And every one of those segments has actuators behind it so that they can all be moved and phased independently. And so part of what we're going to be doing with Webb is we're not launching it and saying, oh my gosh, it's the wrong shape, because we can change the shape. All right. And that's important because we're not going to be able to service Webb. We have to be able to change it in real time, and we can. It's also gold, not silver. And that gold coating is not because gold is expensive. It's coated gold because gold is a highly effective reflector in the infrared. Remember, infrared optimized telescopes. So that's why it's gold. And if you have questions about the mirrors, I can tell you more than you want to hear about what they're made of. They're made of beryllium and why that is. But I have a lot to cover, so I'm going to move right on. So remember, we talked about redder. We talked about invisible light. You can see right through things. And that is true in space as well. So here is a constellation that I bet many of you are familiar with. That's Orion. And many of you who are amateur astronomers know that down here in the belt, down here in the sword of Orion, hanging off of the belt, the three stars, is the nebula, the Orion Nebula. But what you may not appreciate is what that really is a little tiny hole in the dust that allows us to see in the actual nebula. The nebula is much larger than that little thing. That's a hole that allows us to see it's into the nebula. If you had infrared eyes, here's an infrared picture of Orion, and it looks like this. So all of that orange stuff is all part of the Orion Nebula. It's just that right in the end of that little sword, there's a hole in the dust that allows us to see into this little chamber where all these stars are being born. And so we want Webb to be able to actually look in there and look at the dust, look right through this dust and see the stars that are being born. So it's very exciting to have this infrared light, not only to look at the most distant galaxies, but to actually look into these dusty regions. And as I will talk about for the solar system work, there's a lot of really interesting chemistry that we can only see in the infrared. So we'll get to that. It's colder. It has that sun shield. Now, remember the sun shield I showed you? I said it was the size of a tennis court. I'm going to flip it over in this picture so that you see why we have a sun shield. It acts like an umbrella to protect the telescope and the instruments which are behind the telescope from the sun, just like this beach umbrella does, all right? We want this to be super cold. And why do we want it to be cold? Well, here's something that people don't appreciate. When I say infrared light, you're probably thinking about light, but here's a trick. Infrared light is also heat. So if I want to measure the heat from the universe, the warmth from the universe, I have to have a very cold telescope, because if my telescope is not cold, all I'm going to measure is my telescope. That's one reason we don't want to put this telescope Webb on Earth, because Earth is warm. Thank goodness we live here. It's warm enough for us, but it's so warm that it would swamp out the heat from the universe that we want to capture on our sensitive detectors. So we build these sunshades. All right, now, if you're confused about why it's upside down, I'll confuse you even further and show you this cartoon that appeared on Twitter about a month and a half ago. And I saw this cartoon and I'm like, oh, I can't believe it. They obviously didn't talk to anybody from the team when they made this cartoon showing you the sun and the earth and the moon and Webb. Because if they had talked to anybody on the team, they would have actually had it like this, because that's the orientation that Webb will always be. The sun shield will always be between the telescope and the sun, the earth, and the moon. That's what it was designed to do, okay? And one of the things I said, we talked about protection from the sun. I like to show this cute little cartoon because, we're familiar with SPFs, and SPF 30 is good, SPF 50 is better, SPF 100, that's what you want if you're a lifeguard. You don't want your nose to burn. So why don't you just guess in your head, what do you think the SPF of Webb's sun shield will be? I'll give you a moment, and then I'll tell you. It's 1,000,000. It's an SPF of 1,000,000. So it's cutting out 1,000,000, reduces the light to 1,000,000th of the sun that's falling on one side. By the time you get to the other side of those tennis court sides, it's reduced by a factor of 1,000,000. It's a pretty powerful sun shield. Okay, so I said Webb is further. All right, how much further? It's actually, it's about 1,000,000 miles further. It's going to be at a place called the Earth-Sun L2 point. That's a Lagrange 2 point. And we're putting it there because that's far from the Earth and the moon. This picture's not to scale, by the way. If this were to scale, wherever screen you're looking on it, Webb would, first of all, the Earth and the sun aren't to scale, but then Webb would be like a gazillion million miles, like 4 million miles away to the side. It's just a cartoon to show you that L2 is a gravitationally stable point. And we put telescopes. It's not the first telescope that's going to go there. It's going to be in a little tiny orbit around L2. We put it there, first of all, to get it away from the sun, the Earth, and the moon. And second of all, it requires very little fuel to keep it at the L2 point. And that means we can have our telescope up in space longer because it has less fuel to keep it in that little tiny orbit at L2. We can talk about that later if you want. All right, so when we talk about the tools we use, we're going to have cameras and spectrographs. We have 4 instruments on this telescope, and these are the pictures of these 4 instruments to give you a sense of their complexity. This is during their formation stage, when they're on tables and things. They've all since been packaged up and attached to the telescope. They're going to be cameras for taking pictures, so you will get lots of gorgeous images, and there will be spectrographs to take spectra, because that's what the astronomers want, is spectra. All right, here's a picture. This is an actual picture of the instrument suite here. These are the instruments packaged up, being attached to the back of the telescope. So there's the telescope upside down, hanging upside down. Here's some people on the sides for scale. And so I just wanted to show you one of the scarier moments. We've had this thing on a crane above the telescope as it's being connected. It's all done very slowly and carefully. So I just wanted to give you a sense of some of the construction that's going on. So what will Webb explore? I'm going to talk just about one thing today. I'm going to talk about the solar system, but I do want you to know that there are 4 science themes for Webb, and they span the entirety of the universe. Our 4 themes are the first light and reionization. This is a theme to look for the very first stars that formed after the Big Bang. So that's a crucial element that has been driving the design of Webb. After those stars start to form, eventually they start to form into clusters of stars, which we call galaxies. And how do those galaxies form and evolve over time? That's the subject of our second theme, the assembly of galaxies. Within the galaxies, the dust and gas, it starts to coalesce and form more stars and protoplanetary systems. These are things that will turn into planetary systems. So we have an entire theme devoted to that. And finally, planetary systems themselves and the origins of life, both within our solar system and around planets, around other stars. That's the fourth theme. Each one of those themes has hundreds of people working on it and hundreds of science cases. I'm not going to be able to talk about all of that today, but I will focus on the last one because that's my science theme. That's what my team will be working on, and that is exploring the solar system with James Webb Space Telescope. So some people, well, here's a series of pictures of Mars taken with the Hubble Space Telescope. And sometimes my astrophysics friends say things to me like, Heidi, why do you need to use Hubble to look at Mars? Don't we have orbiters and landers and rovers? And I'm like, of course we do. But what you get from a sequence of images like this with Hubble is over time, you can see the polar caps changing. You can see cloud patterns developing and spreading across the planet. Sometimes you can see the planet become enveloped in global dust storms. This is all context material for our rovers that are on the surface and our orbiters, which generally are seeing just tiny swaths of the planet at a time. So with something like Hubble, you can get a complete and global coverage. What Webb will add to this is it will extend us into the infrared. And why that matters is that there are different surface properties. There's chemistry that takes place at night, which is only evident in the infrared wavelengths. And you can map out the dust and the surface at the infrared. You can map out certain organic molecules. One of the questions that's been plaguing Mars researchers for literally decades is, why do we sometimes see methane and other times not see methane? This is true even for our landers on the surface. And so Webb is a tool that will be able to map globally the methane distribution as a function of time over 10 years. And so it might give us some insight into this vexing question of why methane is sometimes there and sometimes not, and why is that, and where is it coming from, and we don't know. That's what we're going to learn. So not only methane, but water and other organic materials. Let me be careful. When I say organic, I don't mean life. I mean carbon-bearing compounds like methane and perchlorates. Those are things that we know are evident on the surface of Mars. All right. So very exciting Mars science. Giant planets, that's what I do. I'm really interested in to know what we're going to see for Jupiter, Saturn, Uranus, and Neptune. Those two bottom small balls are Uranus and Neptune. We're going to do some really cool stuff on Uranus, for example. The little box, first of all, that picture is a picture of Uranus, not Saturn, even though it has a ring. Uranus has a wonderful ring system. And that's a near-infrared image taken with the Keck Observatory. And the colored boxes, the blue, green, yellow, and red boxes, are the field of view of our infrared camera on Webb. And so we're going to get fabulous infrared images of Uranus. I'm very excited about it. It looks from this picture like the camera was designed for Uranus. I kind of joke with my astrophysics colleagues, you made a camera just for me, right? For Uranus. What we're going to do with that camera, not only will we get cool pictures, which I'll be sure to show to you, but we will get these spectra. Now, this is an example of a scientific spectrum. Remember what I said about going down is light that's missing, going up is light that's emitted. And this spectrum of Uranus, this is a model spectrum of what we expect to see with Webb. using a computer simulation, and you can see that there are places where things are missing. That's due to what we think is methane, but there are also places where light is being added, and that is due to molecular emission from warm acetylene and diacetylene and ethane. And so by studying the true spectrum, remember, this is a model, this is what we hope to see, by actually studying what we see on Uranus, if I said Neptune, it's the same thing, we're doing it on both. We want to see how these chemicals change with time and where they're located on the planet. It's going to be a very exciting science return. And there's a young fellow named Lee Fletcher at Leicester University who is leading this for me. And I'll talk about what I mean by that later. But I'm very excited about the Uranus and similar observations of Neptune. Two of the very interesting moons in our solar system are Jupiter's moon Europa and Saturn's moon Enceladus. And what is interesting about both of these moons is that they seem to have oceans of liquid water under their icy crusts. Now, these images that you see here are from spacecraft that have been in orbit or flying by these planets. We won't get images of the moons that look like this, but you see the blue stuff and the purple stuff? That is material that is being ejected from the polar regions of these moons, which we know in the case of Enceladus, we know is nearly pure water because our Cassini spacecraft flew through it. So what we want to do with Webb is we want to be able to point at those areas and try to measure the chemistry in the infrared, which is what's going to tell us a lot more detailed chemistry of what trace molecules there are in that liquid water. And also these plumes, this material seems to vary with time, and we don't know exactly why. We don't know what's driving it, so we hope to learn about that as well. And so here is an example in very detailed scientific language of what I just said to you. Off to the side, you see a picture of the moon with its cracks of where plumes of material are being ejected. And this dotted circle is where we would point James Webb, and we would try to measure with our spectra the chemistry. And so this is a sample of the kind of chemistry we might see in that Enceladus plume, Saturn's moon Enceladus. And the possibilities are amazing. Water, certainly, but methane, hydrogen cyanide, formaldehyde, carbon dioxide, carbonyl sulfide, all of these molecules have characteristic emission lines in the infrared that James Webb will be sensitive to. And so we will be able to explore these questions that are kind of listed there. This is from a paper, but are these bodies rich in this carbon-bearing organic material? What drives them? Are there tidal interactions? Is that what's changing them with time? Those are all questions we're going to be exploring with Webb. Saturn has another amazing moon, the big one in the background here, Titan. And in this background image, it looks fuzzy and sort of kind of orange colored. And that's because Titan is in fact kind of orange colored. It's covered in smog. It's covered in hydrochemical smog. But just like the dust clouds, we can see through dust in the infrared. When you use an infrared camera, Cassini spacecraft had one, and it was able to see right through the dust to the surface of Titan. And you can see that there are surface markings, there are lakes, there's really interesting terrain on Titan. Now, we're not going to be in orbit around Titan, so we will not have this quality of image, but we will be able to do the spectroscopy. And so here's a little map up in the corner showing you the kind of spectroscopy. Each one of these boxes, we can get a different spectrum of the surface. So we can map out a dark spectrum. We can map the spectrum of the dark stuff, the light stuff, the edge stuff. And this spectrum here, the four wavy lines show you a simulation of what we expect, where the black line is what we think the lake reflection would look like. The green line The green line is another basic part of the surface. The blue line is what the clouds may look like. And the brownish line is sort of what the dune structures may look like. So you can see that we'll be able to pull out, even though we won't be able to get the beautiful pictures from this spectroscopy and watching it over time, we'll be able to map out lakes, dunes, clouds on this changing moon, very interesting moon. So very exciting news for Titan. And if you've been paying attention, you know that NASA is planning a mission to Titan. We have a mission called Dragonfly, which is it's like an aerocopter. It's like a helicopter for a quadcopter, like a drone that we're going to launch, send to Titan and go into the atmosphere and then use the drone capability to move around the surface of Titan and look at these different elements. And if we time it right, JWST Webb will be flying at the same time that the Dragonfly quadcopter is on Titan. So it's a really very exciting combination. All right, the Kuiper Belt. The Kuiper Belt is this belt of objects beyond Neptune, kind of analogous to the asteroid belt, but further out and icier. Now, these cartoons across the bottom are just cartoons. We don't know what these objects look like, and we don't know their colors terribly well, with the exception of the one in the middle, which is Pluto. Pluto's the king of the Kuiper Belt. Here is the New Horizons image of Pluto that was taken about 5 years ago, just this summer. And we will not be flying by, so we will not have pictures like this, but say it with me, what will we get? Spectra. We will get spectra of the different regions here, and but use that to look at things that may change on Pluto with time. And that's important because if you look at this beautiful New Horizons image, you see what we call very fresh surfaces, very fresh. And so it could be that there are things changing with time on Pluto. We might see that. So here's an example of the spectrum, because that's what we want. Here's Pluto up the top, but you see this other orange one and this green one. These are other Kuiper Belt objects, and they don't all look like Pluto. So the Kuiper Belt, the different objects have different compositions. And why is that? And what can that tell us about how they formed and how they got to where they are today? And what does that tell us about the formation of our solar system? Those are the questions that we want to answer by using Webb to study almost every Kuiper Belt object that we can get our hands on. So I've told you a lot of things. This is a chart from a paper I wrote not so long ago that shows all the different programs in my program. You don't see my name up there, but I'm the leader of this. As a Webb interdisciplinary scientist, I was selected 18, 20 years ago. I've been working on Webb for several decades now. But as you heard in the introduction, my job right now is I'm vice president of a major organization that runs giant telescopes. So I don't do this science anymore. But what I did, as part of becoming an interdisciplinary scientist, I got about 100 hours of guaranteed time on Webb to use for the solar system. That's what I proposed to do. And so what I did is I reached out to a lot of young people around the world, and I said, what would you do with Webb if you could do something with Webb? And these are the young people that have responded. So I'm divvying up my time, and I didn't talk about asteroids. I didn't talk about comets, but we're doing that. We're going to be looking not only at the things that I talked about, but near Earth objects, asteroids that come close to the Earth, asteroids in the asteroid belt, comets that are far away. If we get another comet like the one we just had that gets really close and bright, we'll look at that too. That's what we mean by target of opportunity comet. We're leaving that open, so whatever comes up after Webb launches, we'll be ready for it. And Mars and many other things. So this just gives you an overview of the things that we are already planning to do. This is just my program. This telescope is open to all astronomers in the world. They can apply for time. It's competitive. You know, You have to write a good proposal. It's going to be evaluated by your peers. If it's good enough, it'll be selected. So there are going to be many, many other solar system things done aside from these. These are just the ones that my team is going to do. But it's going to be a really powerful tool for solar system exploration. And I'm really excited about that. So I started this by saying, this is the science we expect. This is what we have built Webb to do. Knowing the science, not only my science, but all the other science, that's how we defined how to build this telescope, what instruments, what are the capabilities of the instruments. But what we learned from the Hubble Space Telescope is that you build this amazing facility, and there's going to be so many things you haven't even thought of yet. And Webb is going to excel at that as well. And so I don't even know now. I mean, I know what I want to do, but there's going to be a lot of people coming up with some really wild ideas that I haven't even begun to think of yet. And there'll be stuff that we don't know is going to happen. And that's going to be some amazing science too. So it's a discovery machine, really wonderful discovery machine. So is it worth it? This is a little video that we stumbled on about, I don't know, a couple of years ago. It was put together by Hank Green. Some of you who are active on social media may know of Hank and his brother John. They're both authors, but they spent a lot of time sending videos back to them to each other, and they called themselves the Vlog Brothers, video log, like vlog, blog. And one day he did a video about James Webb Space Telescope, and I thought it was really, it kind of encapsulated everything that I just said, but better. So I wanted to share that video with you. So we're going to end with that, and then we'll take questions. So here's Hank Green's video.
Good morning, John. So in my last video, I was to make a video about the James Webb Space Telescope. And then the nerdiest of the nerds in the comments were all, so today, I must talk about the James Webb Space Telescope because it's freaking awesome. But by way of a longer and second introduction to this topic, I have a thing to say. I personally believe that there are two ways to make the world a better place. You can decrease the suck, and you can increase the awesome. Now, these are not mutually exclusive things. That's hard to say, mutually exclusive. But they're also not the same thing. And it's clear that decreasing suck is extremely important, probably, in the end, more important than increasing awesome. And thus, when I talk about the space program, people are always like, NASA's money could be better spent on services for humanity. And to them I say, I do not want to live in a world where we only focus on suck and never think about awesome. If we lived in that world, then people would play soccer by having both teams stand and guard their own goal the whole game, with the ball sitting at midfield. And then at the end of the game, we're supposed to all celebrate because no one scored any goals against our team. That's not going to get you on SportsCenter. We have to guard the goal, and we have to try and prevent bad things from happening. But we also have to make good things happen. And that is why I love the James Webb Space Telescope. It's the space telescope version of a freaking awesome space telescope. This thing gives me serious nerdwood. So without further ado, my nerdy comrades, here are the top 5 reasons why the James Webb Space Telescope freaking kicks ass. It is huge. The total mirror size is 7.5 times larger than the Hubble Space Telescope's mirror. The heat shield is the size of a tennis court. Number 4, it's a freaking transformer. Because it's so huge, it could never fit in its full form in the top of a rocket ship. And so in order to fit into the rocket, it's super duper folded up. And then when it arrives, it unfolds in like 12,000 different marvelous little ways that could go wrong at any moment. And it freaks me out because I worry about that. And oh, woe for humanity. No one is going to be there to see this thing open up. But luckily, the wonderful computer animators at NASA have given us the images that I have been showing you. Number 3, it will operate 1 million miles from Earth. That's about 4 times as far away from the Earth as the moon is. The Webb telescope actually orbits the sun. That's a simplification that's actually in the relative stationary Sun-Earth Lagrange point 2, which I'm not going to try to explain to you right now. If it screws up, there's no way to fix it. You may have noticed that we went to fix the Hubble like 10,000 different times. Well, we're not going to get that opportunity with the James Webb Space Telescope. One chance to do it right, or it's a $6 billion piece of space junk. That is tense. Number 2, it will be able to see planets orbiting stars in our galaxy. Individual planets. If the James Webb Space Telescope was 25 light years away, it could see the Earth. It can also determine the chemical composition of planets, and it can peer into stellar nurseries to see planets as they form. watch solar systems forming. And finally, the James Webb Space Telescope can see 13.4 billion years into the past. This is particularly impressive because the universe is 13.7 billion years old. We will be seeing the first galaxies as they form, the first stars as they form. And guess what? None of this is necessary to life on Earth. None of it's going to help us cure malaria or install a democracy in Egypt, but it is awesome in the truest sense of the word awesome. I'm sorry that there's so many hand gestures in this video. I'm feeling very gestury. This is the dawn of everything that we know. And that is increasing awesome. And that is something that I can get behind. John, I'll see you on Friday.
So I really appreciate Hank's enthusiasm for Webb, increasingly awesome. If you want to learn more about Webb, the Planetary Society has just released a really terrific website called Your Guide to NASA's James Webb Space Telescope. And I've got the link down there, but you can always find it just by Googling Planetary Society James Webb, and it'll probably come up. I encourage you to go there. And so I think I've covered my my talk, and I thank you for your attention, and I'm happy to answer any questions you may have about Webb, its capabilities, and the science that we plan to do with it.
Okay, so we have a couple of questions in the Q&A section. If any attendees would like to ask Dr. Hammel a question, please type them into the Q&A section, not the chat. The chat is only to talk to the general panel for technical questions and the like. So those of you who may have typed in a question in the chat, please cut and paste that over to the Q&A so everybody can see it. The first question we have up is from Rick Bates, and his question is, are we able to focus on the L2 points or any all Lagrange points of exoplanets? It seems like a likely place to look to make a guess about advanced life on the planet. If we can't see that closely yet, will Webb enable us to do so?
Wow, that's a really great and insightful question. The challenge is that seeing exoplanets themselves is extraordinarily difficult. And so we have to work very hard with Webb to be able to see even the biggest, brightest planets close to their host star. The challenge is that the host star is literally like 1 billion times brighter than the planet itself. So then to try to imagine going to the L2 point, what would you put at L2 that would be big enough and bright enough for us to be able to detect it there? I struggle to imagine what that would be. So it's tricky. We're focusing instead on just trying to image planets themselves with Webb. And I have to say that Webb is going to do a great job for certain kinds of planets. I didn't talk really a lot about exoplanet work, but there are some close by exoplanet systems where we look at the planet crossing in front of the host star. And by looking at it crossing in front of the host star, we use the starlight itself to probe the planet's atmosphere and learn about the atmosphere, the exoplanet atmosphere constituencies, like what's it made of? Does it have methane? Does it have water? Or things like that. So it's going to be a really good telescope for that. But I have to say, it's a 6.5 meter telescope, which sounds pretty big, but in professional terms, that's not that big. And we to really answer the question of, is there life elsewhere in the universe? Are there exoplanets that have biological signatures in their atmospheres? We need an even bigger telescope. And we're planning that right now. Right now, the astrophysicists are doing something called a decadal survey. And several of the concept studies for the decadal survey are talking about futuristic telescopes, even beyond Webb, that might allow us to find biosignatures in exoplanet atmospheres. And I'm really excited about some of those. So, yeah, long answer, but hope that you liked it.
Okay, next question. And also, if you would like to ask your question yourself verbally rather than having me read it for you, if you click on the participants button at the bottom of your screen, there is a smaller button on the right side of your screen where you can raise your hand. And we'll get through a few of the typed questions in the Q&A and then start alternating back and forth between the Q&A questions and the raised hands. The next from the Q&A is from Susan Cronenberger, who is asking, what kind of rocket is taking JWST up? Crossing my fingers and toes.
What a super question. So we are launching on an Ariane 5. That is a contribution from the European Space Agency. There was just an Ariane 5 launch about 2 weeks ago, I think, and we all were watching. We always watch, like you, fingers, toes crossed. Ariane 5 has a fantastic track record, and so we are really pleased about that. A little funny anecdote I'll tell you. Originally, we were scheduled to launch on a NASA rocket, and then the European Space Agency said, hey, you know what? We got this Ariane 5. We would like to make a contribution for free. We will give you the Ariane 5 launch, right? And we're like, woo! And then it turned out like for us to use the fairing, that's the rocket thing on the top of the rocket that it goes into, we had to do all kinds of redesign of the spacecraft and integrate it into this Ariane 5 fairing. And in the end, it added about $1 billion to the cost of Webb, our free launch. And so like my takeaway from that is there's no such thing as a free launch. Sorry.
As soon as I catch my breath.
Didn't mean to joke you.
Sadie Coffin asks, is the mirror and sun shield unfurling process all automated once JWST is launched, or will it be controlled in real time?
Yeah, the thing that they showed in the video of it like unfurling and so that is that's all going to be automated, but in stages. We have certain things that happen in a certain order, and so we will be watching the telemetry. We will not have cameras on this, so we won't be able to watch it happening, but we will have telemetry. That's information from the spacecraft being beamed back to Earth. So we will take these things in stages. That process takes a couple of weeks to do all the different things. We will, it's all tightly choreographed, right? But they have pause points so that if something goes wrong with some stage, which it won't, it's all gonna be perfect, but God forbid something goes wrong, they can stop and they can do some assessment and analysis before they move on to the next stage. So we'll be watching every bit of that really very carefully.
Okay, one more question from the Q&A, and then I'll get to the person who has their hand raised. I'm not sure how to pronounce this. Huma Umeda is asking, is it worth being 1 million miles away if astronauts cannot reach it to fix it? Even if you lose some mileage, is it not worth it to put it in a location close enough to be repairable? Yeah,
a lot of dialogue about that. The bottom line, though, is if it's in low Earth orbit like Hubble, it cannot do the infrared science that we want it to do. So you can't do the science close to Earth. All right, Earth is too bright. The moon is too bright. But bright, warm, bright infrared light. So you just physically can't do it in low Earth orbit. You can't do what we want to do scientifically in low Earth orbit. So it does have to be out at the Lagrange 2 point.
Next up is Colin Lyman. I'm going to attempt to unmute you so that you can ask your question.
Hi, my name's Colin. Basically, I'm really interested to know, are there any unexpected or challenges that the general public or people who have been following the Space Telescope would not expect there to be, or would not expect need to be overcome before, the telescope can be put in orbit, or are there any physical challenges, just anything that's interesting, I guess?
Yeah, well, that's a good question, Colin. It sort of depends on where you started to ask the question, when you started to ask the question. When I started working on this project 20 years ago, there were 10 impossible technologies that hadn't even been invented yet. 10 miracles, we called them, that we had to solve before we could even imagine building this telescope. And so, so one of the things you might think about, if you're a layperson, not an astronomer, you might not appreciate how extremely cold it is out there in space, right? We're talking about temperatures that are, minus 200 degrees Fahrenheit, super, super cold. So you have to have materials that are able to withstand that cold. Your electronics have to withstand that cold. And I mentioned those beryllium mirrors. I mentioned the word beryllium.
Mm-hmm.
Why would we use beryllium? It's a very dangerous substance. We use beryllium because it's thermally stable. In other words, if any light from anything lands on these mirrors and changes their temperature, some materials change their shape, and they expand and contract with temperature. And beryllium doesn't do that. Beryllium's very stable, and so that's the reason we're using it for these mirrors, to be thermally stable. What are some of the other kinds of things? Not only is it the outer space cold, but for our longest infrared detectors, where we're really trying to measure super long wavelengths, we actually have to cool the instruments themselves even further. And we're cooling them using something called a cryocooler that takes the temperature from not just the ambient space temperature of minus 200 degrees, but we're cooling them almost to absolute zero. And we're doing it on a flying spacecraft. And that's really hard to do. And that was another couple $2 billion of why this is an expensive telescope. It's kind of hard for me to take a step back to figure out what kind of questions people might not know. It's just, we've never built a segmented telescope like this for outer space. That's brand new. We've never put a telescope with adaptive optics into space. That's brand new. Many, many aspects of Webb are brand new, and that's what makes it scary and also makes it intrinsically truly exciting. It's sort of like Hubble 30 years ago. We had never put a telescope like that up in space for civilian use to study the cosmos. So, it's just, when you're doing something for the first time ever, it's hard. And you encounter lots of challenges that you didn't expect. And that's certainly been the case with been the case with Webb over the last 20 years.
Yeah, that's really interesting. Thanks.
Yeah.
Okay, the next question is from Claudio Veliz. Is there a metric by which the general public can appreciate the increase in IR and spectral sensitivity of the Webb over what our best facilities are able to detect at this time?
A metric, huh? Gosh, we have lots of charts and graphs and things. I didn't show a lot of them because I didn't want to throw too much sciencey stuff at folks. Let me see. How can I put this? Well, I think one way I'll try to put this is that the other telescope we have that works at infrared wavelengths is the Spitzer Space Telescope. It's just starting. It's recently been decommissioned, and Webb is it's 3 times larger, which means it has almost 10 times the area. So in terms of sensitivity in the infrared, it'll be, a factor of 10. In some wavelengths, a factor of 100, better than we've ever done before. Another thing that's kind of hard to put into layman's terms, but it's really crucial for our space telescopes, is something we call stability. Telescopes, we have big telescopes on the ground. I've used the Keck 10-meter telescopes. They're huge telescopes, bigger than Webb, all right, but Keck, even our bigger telescopes have to look through Earth's atmosphere, and Earth's atmosphere is kind of always swirling and shimmering and moving, and even on the most pristine places on Earth, you still have to look through the atmosphere, and so you don't get really stable, pure images that have no variability. The images are always varying a little bit. when you're in space, like with Hubble or with Webb, you don't have that atmosphere. So you don't have any of that wiggliness and turbulence and perturbation. So the stability is rock solid, and that's crucial for certain kinds of observations. Like we talked earlier about looking at planets around other stars. You need ultra stable images to be able to cleanly separate a planet from its host star. And that's what space telescopes with their no Earth's atmosphere excel at. And so, although I don't have numbers for you, there's a reason that over the last 20 years, we get asked, it's been 20 years, are you sure you still need James Webb Space Telescope? Haven't your ground-based telescopes gotten better than Webb? And the answer is they haven't. They just can't do it from the ground. We need to have these facilities in space to have the stability. And the stability gets us the sensitivity, and it gets us this infrared wavelengths we just can't do from the ground. So if you really, really want to dig in, if you're interested, if you're a student who is interested, or if you're a researcher who might want to use Webb, we have a lot of websites that have all this information on the websites with all the charts and graphs and numbers that you could ever want. So that's where I would send you.
Okay, next question is from Ming Chi Zhong. With Webb, where do you think we will be a decade from now?
Ooh, gosh. That's a great question. I think we will have learned a tremendous amount about the infrared universe that we don't know right now. We will have discovered certainly the first galaxies. We will have seen what we think are the first galaxies to form. We may have detected the first stars. We may have detected the chemical compositions of atmospheres around the closest 10 exoplanets. We may know if there is evidence in the plumes of Europa and Enceladus of whether there's a possibility of organic life in those oceans under their icy crusts. I mean, it's a huge array of possible science. It's hard for me to know exactly which of these things are going to be the most exciting, but the possibilities are mind-boggling to me right now. So I hope I hit a few things that interested you.
Okay, the next question is from one of our own students here at the Dublin School. It's Lucy Walton who asks, will Webb interact with black holes at all?
Great question. Well, so certainly with Webb, we will be looking at the cores of nearby galaxies. Although you can't see a black hole, you can see the influence that a black hole has on its surroundings. And so, for example, in the center of our own galaxy, we know there's a black hole there. We can't see the black hole, but we can see stars in orbit around it, whizzing around it. And so with Webb, we'll be able to look at the cores of other galaxies and learn about the dynamics in those other galaxy centers to learn about the presence of black holes there. And so, yes, black holes are definitely going to be on the list of targets for Webb, for sure.
Okay, we have 3 more questions pending. This next one is from Sadie Coffin, who asks, what is the biggest unanswered question we have about Uranus and Neptune that JWST might help us answer with spectra?
All right. Well, I mean, I could give you a whole hour-long lecture about that, but I'll try to give you just one example. One of the things we've learned about Uranus as we've been studying it with Hubble and Keck in the 30 years since our only flyby mission of Uranus, we've learned that the 2 hemispheres of Uranus seem very different. And we don't understand why that can be. We think that there may be compositional variability from one side of the planet to the other, like from the north to the south. But we're not sure because it's very difficult to measure this on Uranus because Uranus is so far away that its disk in the sky is only what we call arc seconds. For those of you who are astronomers, you know what I mean by an arc second. It's very, very small, and it mostly on the Earth, our atmospheric smear from our atmosphere smears things out like about an arc second. So Uranus is very hard just to resolve at all. So this question of, does the chemistry vary across the disk? Does the chemistry or temperature vary across the disk? We can't do that. We want to know. I want to know this. Been thinking about it for 30 years now. Same with Neptune, except Neptune's even harder because Neptune is much further than Uranus. And so its disk is only 2 arc seconds across. So the question of what is the chemistry in the upper atmospheres? How does it vary as a function of time? How does it vary on the planet itself? These are really basic questions that you'd think we'd know, but we don't. We don't know. And so that's the kind of stuff that I hope we pull out of James Webb for Uranus and Neptune. Plus, I want to send a mission there someday. Yeah, to both. Or either one. I take one.
Okay, the next question is from Frank Winkler. Could you talk a bit about the projected timeline for JWST? When is it due to launch? When will scientific observations start? What is its projected lifetime?
Great question. So the current launch date is late October of next year, 2021. After it launches, it takes roughly from the time we launch to the time that we're fully stable in L2 with all of our instruments fully checked out and have been fully commissioned. We've checked out all their modes. That's about a 6-month time gap. All right. So it'll launch and it'll be traveling. And then once it gets to L2, then we have to check out every instrument so that's all 6 months. So then after we start the full observations, the lifetime that we've scheduled to, that we've designed to, we've designed it for a 5-year lifetime, but we have enough expendables on the spacecraft to last for 10 years, and maybe even more if we can be extremely clever about how we use those expendables. And your question will then be, what are the expendables? Like, what do you need to carry? And the answer is, you need to carry fuel for station keeping. We have little rockets that keep us in that orbit around L2. And that hydrazine that we use for station keeping is the expendable. When we run out of the hydrazine, we will no longer be able to maintain our orbit, and then we will no longer be able to do observations. But we're hoping that we'll be able to get the full, certainly the full 5 years guaranteed lifetime, and we're hoping to get another 5 years of extended lifetime for Webb. So 10 years total.
Okay, next question. Another one from Lucy Walton asks, which planet is the closest to being suitable for human life that has been documented so far?
Oh, do you mean in our solar system or in exoplanets?
I'm going to guess either.
Okay, well, in our solar system, I mean, the planet none of the other objects in our solar system are suitable for hosting human life. I think you all know that. Mars has a very, very thin atmosphere, which we can't breathe. People talk about terraforming. I'm not sure we want to go there. And none of the moons are suitable. Titan, which I did talk about, actually has a thick atmosphere. Its atmospheric pressure is about a bar, which is the same atmospheric pressure we have here. And it's a nitrogen atmosphere too, kind of like we have, but it does not have the oxygen that we need to breathe. And so, it would not be a good place to live. So there's no planets in our solar system that are suitable for human life without extensive engineering of domes and habitats and things like that. What about exoplanets? Well, that's a really good question. And that's the holy grail, isn't it? We'd like to know, can we find an Earth-sized and Earth-like planet around a sun-like star at the right distance that might have liquid water, which is what we know is necessary for life as we know it. And so many of our projects in astronomy right now are geared towards finding which planets are the most likely to be Earth-like, Earth habitable. And if you really want to know the answer to this question, there's a website, and I drawing a blank on it right now, but you're probably a clever young person and can probably find it with the clues I'm giving you. They developed a habitability index that's based on things like how big the planet is, how close is it to its host star, so what distance does it put it at a distance where it could be habitable, and they rank all of the known exoplanets with a habitability index. And so, we're looking for one that's like habitability index 1, I mean, just like the Earth. We haven't found that one yet. Some of the planets in the TRAPPIST-B system are interesting. That's an exoplanet system that has like 7 planets that are all kind of Earth-like and in size and all kind of the right distance from their host star to maybe have water. They're interesting. If we ever build one of these advanced space telescopes, like I mentioned, they'll certainly be on the target list to be explored, to explore their chemistry, to see what the chemistry of those atmospheres are like. But it's a question that so many of us want to know the answer to right now. Is there an Earth 2.0 out there? Is there an Earth-sized planet around a sun-like star at the right distance that might host life like we know it, that we might be able to go someday once we invent warp drive? It's within our grasp to actually answer that question right now. And that's why so many of us are very excited about Webb and what it will teach us, and then what the next generation of Space Telescope, what it can teach us as well. Because I think we can answer this question like before I die. Before I get a mission to Neptune, we might actually know if there is a biosignature on an exo-Earth. It's there. It's possible. It's exciting.
Okay, so more questions are coming in, and we actually have one from our local audience, which is, will JWST's infrared capabilities be able to study the cosmic microwave background radiation? And if so, what could it do that previous systems could not?
Okay. So the super short answer to that question is no. We don't see the cosmic microwave background radiation. It's in the name, microwave, cosmic microwave background. You have to be looking at microwave wavelengths to see that. And we are not going to go that far into the infrared. That's a totally different design of telescope. We've already actually, what we know about the cosmic microwave background comes from other telescopes specifically designed to study those wavelengths, like the Kobe spacecraft, which incidentally was at L2, kind of like Webb. But that's a very different kind of instrument, and we're not designed to do that. So if there's sometimes when you sort of make timelines of the universe from sort of like the Big Bang, and then there's the cosmic microwave background, and then there's what we call the epoch of reionization, and then there's the first stars. So we get back to the first stars, but we don't get into that cosmic microwave background. So remember in the beginning, I said something about we have different telescopes at different parts of the spectrum because different parts of the universe emit different colors of light. Well, this is exactly that point. We don't see microwave. That's why we built microwave telescopes. And we won't be able to probe that question. Sorry. Can't do everything.
Okay, another question from Claudio Vellis. Is the limit of the Webb's visibility back into the earliest era of the universe impacted by the ambient temperature at the 80 to 100 million year era after the Big Bang?
I'm not entirely sure of the answer to that question. Because that's not my field of study, I don't have it at the tip of my tongue exactly what that timeline is in that period near the Big Bang to first light. You'd have to have a different speaker talk to you about that. Sorry.
Okay. Anonymous asks, could you talk a bit about why the Hubble Space Telescope lasted way longer than expected? And is that the main reason JWST's launch was delayed all of those years?
Sure. So one of the main reasons that Webb has been a powerhouse cutting edge facility for over 30 years is that it was in low Earth orbit. As one of the earlier questioners pointed out, why don't we put Webb in low Earth orbit? I already explained we can't put Webb in low Earth orbit, but Hubble is a visible wavelength telescope, and so it's not affected by the Earth's heat and the moon's heat and things like that. So it's just fine in low Earth orbit. The design of Hubble was wedded to our space shuttle program back in the 1980s. And they were kind of a symbiotic relationship. Some aspects of the shuttles were designed to accommodate Webb. Webb was designed to be put in a shuttle to be launched. And what that meant was that because it was in low Earth orbit, we could send astronauts back up to Webb to service it. And it was actually designed to be serviced. If you ever see pictures of the astronauts working with it, it has like doors that open that allow you to get inside to the instrument. The instruments themselves were modular to slide in, and they could be pulled out, and then new instruments could be slid in. And so it was designed with a serviceable capability in hand. And so we didn't just... the way we talk about this is we haven't had just one Hubble. We've had Hubble with one mirror, but we've had 5 different servicing missions to it. And during each servicing mission, old components were taken out, new components were put in, new computers, new cameras, new spectrographs. And so we rejuvenated Hubble multiple times over the course of its life. Our shuttle program in the United States ended, after the last servicing mission, 2009. That was the last servicing mission, and Hubble has not had a servicing mission since 2009, and it is still remarkably robust. Knock on wood. I'm knocking on every bit of wood I can find within my grasp here. It's an old spacecraft now. Things go wrong with old electronics, but so far Hubble's been really hanging in there. It's not going to last forever. I remember a couple of years ago, we were talking about our Hubble 2020 plan. Well, now here we are in 2020, right? And we're like, nearing the end of 2020, and Hubble's still going strong. So it was designed to be long lasting. NASA has a tendency to super engineer things really incredibly well. Same thing with its Mars rovers. There was a Mars rover, it was landed, it was supposed to last for 30 days. And, 3 years later, it's still going. So, we talked about, why didn't you make Webb serviceable? Well, we don't have any way of getting to L2. We can't even go back to the moon. At this point, we can barely get to low Earth orbit. So where we had to send Webb, there was no way of being serviced. So we didn't make it serviceable. When we're talking about our future space telescopes now, like things beyond Webb, if they are amenable to servicing, we talk about that because I and probably you can imagine a future where we do have the capability of launching astronauts again, and we have the capability of them doing extravehicular activities like the astronauts did for Hubble. And so I can imagine that. And I'll throw this out there too. We don't totally give up on servicing just because we put things at L2. We talk about maybe we can imagine robotic servicing. We got really smart people at our NASA centers. And so, we don't totally rule it out. When I said, we run out of hydrazine, maybe we can go out and refuel it. Maybe there's after it's died, why not try it? Maybe bring it back to life. I don't know. We'll see. So I hope that answered your question. It was a little bit long-winded, but I hope I got it.
Okay, we have one more local question and then one more in the Q&A. Could you describe what a Lagrange point is? So what L1, what L2?
Yeah, sure. Yeah. So you can imagine, I'll do it with the Earth and the sun. So you can take, here's the sun, here's the Earth, right? You can imagine that there's a point kind of close to the Earth where the gravitational pull of the Earth is the same as the gravitational pull from the sun, right? Even though the sun's real big and the Earth's real small, if you put it close to Earth, there's a point where their gravitational pull for both is the same. And that's the L1 point. And if you put a thing there, if you put a rock there or a telescope there, it'll stay there, right? Because it's not going to go to the Earth and it's not going to go to the sun because it's balanced. You with me so far? I'm kind of looking at you, Eric, because you're the only person I can see on the screen. So I'm hoping you're understanding that. All right. So that's L1. But there's actually, if you think about the math, there's another point if you keep going on the other side of the Earth, where the pull from the sun is equal to the pull from the Earth. Now, they're both pulling the same way, right? But they're equal. And so if you put your spacecraft in a little tiny orbit around that point, that L2, which is the same gravity from the Earth as the gravitational pull from the sun, it's what we call a gravitationally stable point. And so it requires much less energy to stay in that little point than it does over here or over there or down here. In any of those other places, the pull from the sun or the pull from the Earth will dominate and you will not be in a stable situation. There are other Lagrange points as well. It isn't just one, which is between the two objects, or two. There's also a 4 and a 5 that are, equidistant. There was like a triangle, if you remember the chart. All of those are slightly stable. And this is a really very real effect. I mean, we know this because we don't need to do it with telescopes and spacecraft. If we look at, say, Jupiter, and we look at the sun and Jupiter, we can see that at the L4 and L5 points, which are those gravitationally stable points, there are little objects, little asteroid-like objects, little moonlets that have actually been, just by chance, drifted into that region and then stayed there because it's a gravitationally stable point. And so as Jupiter goes around the sun, these clouds of little moonlets at the L5 and the L4 points, they just travel around the sun with Jupiter. They orbit, but they're trapped in these gravitationally stable points. We call them Trojans, Trojan asteroids. And we see Trojans for Saturn and Uranus and Neptune as well. So these gravitationally stable points are not just like an artificial thing we made up for spacecraft. They're a physical thing in the universe. And they happen whenever you have two bodies. I was talking about Earth, the Sun-Earth Lagrange points, but there are also Earth-Moon Lagrange points. So people who are talking about doing lunar exploration and lunar settlements, they talk about the Earth-Moon Lagrange points in the same way, that those are places of interest. Hope that was clear enough through hand gestures and Zoom.
So the final question in the Q&A here is from Julius Medulla. When you talked about station keeping, were you referring to keeping the same orbital plane / velocity, or were you referring to changing the orientation of where JWST is pointing to?
Oh, good question. Yeah, that's no.
It was a little bit more. If not the latter, is JWST also using gyros to change orientation like Hubble did?
Yeah. That's a good distinction. I'm glad you caught that. The station keeping with the hydrazine is to keep the spacecraft in the orbit around the L2 point. All right, so it's got a little orbit there. But then for the pointing of the telescope, we use reaction wheels like Hubble does. So we have a separate thing, and keeping the angular momentum conserved in our reaction wheels is really important, and that has an effect on how we do the pointing and acquisition of stuff in the sky. So that was a good call. Those are two very separate things, and the hydrazine is only for keeping the spacecraft in its L2 orbit. Reaction wheels are used for the pointing of the telescope at celestial objects.
It appears that we are out of questions. So last call to any attendees. assuming Dr. Hammel, if you have any additional time. Okay, well, I'm not seeing any.
We have a hand.
Oh, excuse me, we do have a hand. Colin Lyman again. You should be unmuted.
Hi again. Real quick, I just wanted to ask if like there are also small clouds of asteroids and other objects right around, like in Earth's Lagrange points and like between it and the moon and it and the sun and all that.
Yeah, typically these little guys collect in the L4 and L5. So one of the things we did do, we talked a lot about how clean L2 really is. To your point, is there dust there? Is there debris? And based on the experience of the other spacecraft that we've already put into L2, the COBE spacecraft, the WMAP spacecraft, we have a pretty good idea that they're pretty clean of this sort of orbital debris, because we worry about that, right? You worry about those giant sun shields and big mirrors, and you don't want it to be hit by asteroids and stuff like that. And we think we're okay. We think we're all right.
Cool.
Yeah.
Yeah, it's really nice. Okay. Thank you so much.
You're welcome.
Okay, that appears to be it for the questions. So on behalf of Severa and Middlebury College, I'd like to thank you, Dr. Hammel, for giving your time. We'd like to also thank Jonathan Kemp of the Middleman Observatory and the Middlebury College for his generous hosting of this virtual event, and Ginny Sigia of the Southern Vermont Astronomy Group for bringing this all together and being the communication link that made it happen. Thank you to our attendees for taking the time to listen and for your great questions. We are working on putting on a series of these virtual talks, so if you'd like to keep an eye out for that or sign up for our respective mailing lists, you can go to the links that we're going to be posting in chat for Severa and Middlebury College. Severa's next monthly virtual meeting will be taking place at 7 p.m. on Tuesday, October 13th. Our guest speaker will be Tom Fields of Field Tested Systems, who will be giving a presentation on spectroscopy, which is a wonderful tie-in for tonight's subject. But he will be focusing on tools and techniques more accessible to the amateur who doesn't have several $billion lying around. So thank you all for your attention, and we hope to see you all again next time.